Hey guys, welcome to homework 26. I'll go ahead now to share the homework for this class. Okay, I hope you guys can see this. The first problem here says focus on concept question 06. The refractive index of a material A is greater than that the refractive index of material B. So A is greater than B. So you know when the light is traveling from a lower refractive index, say air, to a higher refractive index like glass, the incident ray that goes in, the angle of incidence becomes greater than the angle of refraction because it's going to bend in the higher refractive index medium. So the more dense medium, the light will bend in, the less dense medium, the light will bend out from the normal. So that's how you can tell. So if A has a higher refractive index than B, so they give us some drawings, and the dashed lines denote the normals. Which of the drawings shows a situation that is not possible? So reflection is possible. We can have partial reflection, even if there's greater or traveling from a greater to a lesser or lesser to a greater. So A has a larger refractive index than B. So the angle of incidence here is greater than the angle of reflection. That is possible. This is correct. For number 4, A is larger than B. So you see the angle of incidence here is smaller than the angle of refraction. You call it the angle of emergence, if you like, if it's coming from 3-step location. But the point is, the one that has the angle closer to the normal has to be A if there's refraction. If there's reflection, like in this case, the angles are equal. So these 3 are correct except 4, because A has a larger angle than B to the normal. So this will only happen if B has a greater refractive index than A. So this is not possible. So drawing 3 is the one that's not possible. Okay. Chapter 26, problem 01 says a plate glass window with refractive index 1.5 has a thickness of 3.2 millimeters. How long does it take light to pass perpendicularly through the plate? So we're going to combine 2 formulas. Refractive index is speed of light in air over speed of light in the medium. And then time taken is distance over speed. So instead of speed here, we'll have refractive index over speed of light. So we do refractive index over speed of light for V here. And then we put our D on top. And then we finish here for, speed of light over refractive index is V here. So we just put in the parameters here and then we're done. Okay, next, amber refractive index 1.546. That's chapter 26, problem 14. It's a transparent brown yellow fossil resin. An insect trapped and preserved within the amber appears to be 1.4 centimeters beneath the surface. So when viewed directly from above, how far below the surface is the insect actually located? So they are looking for the real depth. So we know refractive index has several formulas: wavelengths ratios, speed ratios, real depth over apparent depth. So the real depth over apparent depth is the ratio of the refractive indexes also. So the real depth becomes equal, is that okay? The ratio of the indices, N1 over N2 from, this is the one inside the amber, and this is the one inside the air or vacuum, if you like, is approximately 1. And then the distance that is observed, is that okay? That appears the apparent depth is 1.4. So you put that so you get the real depth. So you see it's actually deeper. 2.2 is deeper than 1.4. It's deeper than you see because refraction makes it look closer to you. Okay, chapter 26, problem 18 says, right here. A stone held just beneath the surface of a swimming pool is released and sinks to the bottom at a constant speed. What is the apparent speed of the stone as viewed from directly above the observer who is in air? So you're going to see real speed over apparent speed is also a ratio of the distance traveled. And then you can use those distance traveled or the depth that you see under that, which is not given. We only have speeds. So we're going to use these speeds and get refractive indices. So instead of V over D, we're going to use D prime as D N2 over N1. This we got from the previous slide. Real depth times N2 over N1 was our apparent depth, D prime, remember. And then from here, we get V to be D cancels D N2 over N1 times V. So the ratio, this is just like a derivation. V prime over V is N2 over N1. So you get V prime to be V N2 over N1. And from there, you can get the apparent speed of the storm. Okay. So you're going to see it slower. The real speed is 0.64, but the apparent speed is 0.48 meters per second. Okay. Channel 26, problem 28 says a point source of light is submerged 2.5 meters below the surface of a lake. So the distance from here to here is 2.5 meters. This is just a diagram I put here to illustrate what's going on. On the surface of the lake, directly above the source, the area illuminated is a circle. So we have exactly the same thing on the surface of the lake right there. So what is the maximum radius that this circle could have? So when light is traveling from a denser medium like water, is that okay, outside to a less dense medium like air, that's where there's a probability of having a total internal reflection, because this angle is small. When you come out, it gets larger. So there's a particular angle you get to here, the light comes to this number 3 line, it's on the surface. That angle is called the critical angle. Anything beyond the critical angle, you have total internal reflection. So the largest you can get is the critical angle just before total internal reflection. And we know how to calculate critical angle. Sine critical angle is N2 over N1, that is refractive index of medium 2 over refractive index of medium 1. Medium 2 is the air, medium 1 is the thick medium. So air over water, refractive indices, sine inverse of that gives you critical angle. Then this critical angle is right here. They want this radius, this distance of this circle from here to here. We know this height. So tangent, opposite of this critical angle over adjacent, the height, the depth, 2.5. So equals tangent for 48.6, critical angle. So the radius becomes 2.5 times tangent 48.6, and you get the answer there for the maximum radius that this circle can have. Okay, next problem is chapter 26, problem 31. It says the drawing shows a crown glass, refractive index is that, with a rectangular cross section as illustrated. A laser beam strikes the upper surface at an angle 60 degrees. After reflecting from the upper surface, the beam reflects from the side and the bottom surfaces. If the glass is surrounded by air, determine what part of the beam first exits the glass. Is it at point A, B, or C? So there is air around this glass. And then repeat this if the glass is surrounded by water. So we're going to do some calculation here. So this is 60 degrees coming. So if this 60 degrees is greater than the critical angle, then there's going to be total internal reflection. So nothing will go out here. If 60 degrees is not up to the critical angle, then light will pass out of A. So what we need to do is, using the glass-air medium, glass-air interface, let's find the critical angle for glass-air interface. If it is greater than 60 degrees, then it means that this light will not reflect, it will pass. If it's less than 60 degrees, then this light will refract and go pass to the other medium. So critical angle for air glass medium is refractive index of air over refractive index of glass, sine inverse. You get that 41 degrees. So 41 degrees is less than 60 degrees. Is that okay? So it means that it will, at what you're seeing right here, the light will be totally reflected at point A, since the incident angle of 60 degrees is greater than the critical angle. So because 60 degrees is greater than the critical angle, any angle more than the critical angle, you have total internal reflection. So the angle here is 30 degrees to make 90 degrees. So this 30 degrees is less than 41 degrees. So this one will pass out. So for air glass medium, point B is where the ray will go out. Then for air glass water interface, not air glass, water glass interface, we calculate our critical angle again using water surrounding glass instead of air surrounding glass. We get critical angle greater than 60 degrees. So since 61 degrees is greater than 60 degrees, and 61 degrees is the critical angle, so the light coming from here will pass through A for sure, because it hasn't gotten to the point of total internal reflection yet. It has to get to 61 degrees for you to hit the interface for total internal reflection. Okay. Chapter 26, problem 45. Sorry. It says, a beam of sunlight encounters a plate of crown glass at a 36.30 degrees angle of incidence. Crown glass has n equals 1.520 for red light and n equals 1.538 for violet light. Find the angle between the violet ray and, so we're going to use Snell's law here. N1 sine angle of the medium 1 equals refractive index of medium 2 sine angle of reflect or refraction of medium 2, or the angle the ray makes at medium 2. So from here we can find sine theta 2 using N1 as air and 2 as the crown glass. So N sine theta 2 is N1 over N2 sine theta 1, where theta 1 is the angle it makes in air, angle of incidence in air, just at the crown glass. So we find the angle of refraction in crown glass to be 22.64. We do the same for the red ray. So okay, this is for the violet. So for the red ray, we do the same thing. We get theta 2 angle to be 22.92, and then we just find the difference. We find the difference in the between the rays. Okay. So focus on concept question 11. So this one says that an object is situated to the left of a lens. A ray of light from the object is close to the and parallel to the axis of the lens. The ray passes through the lens. Which one of the following statements is true? Is that okay? So we all know this is the definition of the focal point. We've seen this several times. So the correct answer here is C. The ray passes through a focal point of the lens only if the lens is a converging lens. So the other ones are not correct. It doesn't pass the lens no matter wherever lens, whether converging or diverging, no. Okay, because the object is situated to the left. Is that okay? To the left. The ray of light, you know, when the object is to the left, for a diverging lens, the image is virtual. And for a lens, a virtual image the same side as the object. So it won't pass through like that. It will form an image in front. So the correct answer here is C. Okay. Next question, focus on concept question 12 says, what type of single lens produces a virtual image that is inverted with respect to the object? No lens. All virtual images produced by a concave lens or a convex lens are always upright. For a concave lens, which is a diverging concave lens, which is it's called converging mirror, and convex lens is diverging mirror. Okay, so when we have a concave lens, a convex lens, which is a converging mirror or lens. I keep mixing the lens and the mirrors. But we know a convex lens behaves like a concave mirror, and a concave lens behaves like a convex mirror. So that is how I remember both of them. So when you have a concave mirror, which is a convex lens, which is also called a converging lens, when you have a converging lens, it forms a virtual image only when the object is between the focal point and the lens. And it's always upright. And a diverging lens forms a virtual image no matter where you put the object, and it is virtual and also upright. So there is nowhere you have a lens producing an inverted virtual image ever. They are always upright. One is magnified, one is diminished. Focus on concept question 13. What kind of image can a single converging lens not produce? There are many options, but the correct answer is a virtual image that is upright and smaller with respect to the object. That is the correct one. All the other ones and the options are possible, depending on the location of the object. But a converging lens always produces, when it produces an upright image, that image is virtual, and that image is large, is magnified, is larger than the object, so it's never diminished. It's only a diverging lens that produces a virtual image that is diminished. Okay. Chapter 26, problem 51. A camera is supplied with two interchangeable lenses whose focal lengths are this and that. A woman whose height is this stands 6.4 meters in front of the camera. What is the height of her image on the sensor as produced by this lens and that lens? So here we're going to do some formulas first to understand. So we know magnification formula. Image height over object height is negative image distance over object distance. From here we get image height in terms of the rest. And then from the mirror formula, from here we get image distance to be this from the mirror formula. After solving for di, we get this. Now put this di here for hi. So hi becomes h naught minus di over d object is h naught minus 1 over d object. Then di on top becomes this guy. So which is this after canceling terms. So this is HI, image height, after solving, putting these two formulas together, we get this final. So we're going to use this now. Is that okay? Given the height of the object and the focal length and the distance of the object. So we're going to go to the next. So we'll do for the first mirror where the focal length is 33 millimeters. We get our answer. And then we go to the second mirror when the focal length is 120 millimeters. We get our answer for image height, basically. So the first step is deriving that formula and then using this to simplify. Okay, and say both heights are negative because the images are inverted with respect to the object. Okay, next, chapter 26, problem 52 says, when a diverging lens is held 16.2 centimeters above a line of print, as in figure below, the image is 7.1 centimeters beneath the lens. Is the image real or virtual? What is the focal length of the lens? So this is really easy. From here, we get the image object distance to be that. Image distance is negative. Is that okay? Because it formed 7.1 centimeters beneath the lens. So the image is formed the same place of the object. So it's a virtual image. So the object is here, you are here, the image is also beneath the lens. So it's a virtual image. But it's a diverging lens, so you expect that your image distance will be negative. So from here, I use the mirror formula. I find my focal point to be that, and then I just put my values there, and it gives me minus 13 centimeters. This centimeters in the unit. Okay. Okay. And the last problem, chapter 26, problem 60 says when the converging lens is used in the camera, the film must be placed at a distance of that from the lens to record an image of an object that from the lens. So here they're asking you to just find the same length is used in a projector. So the first part is to find the focal point of this length, given the object distance and image distance. Now use that focal length you've gotten, the focal length you've gotten, use it to find the object distance for a projector with a given image distance of 0.43. So find focal length with image distance and object distance given for the camera, then use the same lens for a projector, knowing the focal length and the image distance, find the object distance, and that's how you solve this last problem. Thank you guys. I'll see you guys next week for next homework, and have a good one.